Hi there! I'm making this video from the University of Tulsa in the United States, where I'm studying this little device, the muscle-like actuator. Now, it may not look much like an actual muscle, but it does share two very important properties with our muscles. One is elasticity, the other is redundancy. The muscle itself is inherently elastic, and so is the tissue that connects it to the bone, the tendon. Tendons play a major role in locomotion. The Achilles tendon alone, for example, helps conserve around 1/3 of the energy during running. Redundancy is present in the form of multiple parallel strands of muscle fibers. Each of them individually contributes to the output force generated by our muscle. Furthermore, individual muscle fibers are made up of sarcomeres. These are tiny contractile motor units in series. The more sarcomeres are recruited, the more the muscle fiber contracts. Apparently, years of evolution have led to the conclusion that elasticity and redundancy are desirable for the human actuation system. There are indeed many potential advantages to elasticity and redundancy. The actuators become safer and more robust against failure, they can have a higher power density, and they can be more energy efficient. And it is precisely the energy efficiency of elastic and redundant actuators that was the focus of my PhD thesis. Let's first have a look at how elasticity can be implemented in actuators. In mechatronics and robotics, operating cycles often exhibit both forward and reverse power flow. As the power flows back and forth between the power source and the load, we encounter drivetrain components, which each cause energy losses. Overall, actuation becomes very inefficient. This can be improved with elastic elements. Here's an example of how this works. On this setup, between the motor and the output link, we have two antagonistic springs, creating a series elastic actuator. The motor forces the link to follow a sinusoidal trajectory. We can see that the output link oscillates nicely with an amplitude of 45 degrees, while on the other hand, the input side is nearly standing still. In other words, the motor speed is near zero, and so is the mechanical power it provides. The reason why this works is because springs create a direct path for power exchange with the load. This way, the power flow through the lossy components can be reduced, and the overall efficiency of the actuator will improve. Note that the spring can also be placed in parallel with the drivetrain instead of in series. The principle remains the same. Power exchange between the spring and the load reduces the power flow through the drivetrain. This manifests itself as a reduction in the torque borne by the motor, in contrast to the speed reduction offered by series springs. Now, so far, we've only talked about mechanical power. What we really care about, though, is the power that we're drawing from our batteries, which is electrical power. Now, this is where the story gets more complicated. Typical drivetrain components, such as gearboxes and motors, exhibit speed and load-dependent efficiencies. Moreover, these components also have an inertia, which can have a strong effect on system dynamics and power flows. In my PhD, I have shown that, in robotics and mechatronics, electrical power flows are indeed very different from mechanical power flows, not only in amplitude, but also in shape. Only speed and load-dependent models can predict these power flows and the actuator's energy consumption. Interestingly, despite this evidence, many researchers still optimize elastic actuator designs by minimizing the mechanical power flow through the drivetrain. This can sometimes lead to suboptimal solutions. Active ankle prosthetics are a good example. An active ankle prosthesis requires around 250 watts of mechanical peak power to provide push-off during walking. Implementing a well-tuned series spring, however, can reduce the power flow through the actuator considerably. When optimized for minimal mechanical power flow, the peak power can be brought down to approximately 120 watts. But the electrical power tells a different story. High power peaks emerge in late stance and early swing due to the combined effects of the spring and the drivetrain's own inertia. By optimizing the design with an appropriate drivetrain model, this effect can be reduced and the overall energy consumption improved. Now, which of the two basic topologies is more energy efficient? Is it the series or the parallel topology? There are many different opinions among researchers, which sometimes lead to intense debates, but General guidelines simply do not exist. In search for answers, I studied both actuators on a simple setup, the pendulum that you saw previously in the video. In simulations and experiments, I looked at both the mechanical and electrical energy consumption of the actuators for a wide range of stiffnesses and oscillation frequencies. Interestingly, the optimal stiffness for the series springs was roughly the same in both cases, while for the parallel springs, the optimal stiffness for minimal electrical energy consumption was higher than for minimal mechanical energy consumption. Series springs appeared to do better at high frequencies, especially in terms of electrical energy consumption. However, this result can easily be changed by adding an offset to the imposed motion. This is more or less equivalent to adding a constant to the required torque. As the offset, and therefore the constant torque, is increased, the energy consumption of the series elastic actuator increases drastically, while that of a well-tuned parallel elastic actuator remains roughly the same. This is because the equilibrium angle of a parallel spring can be tuned to compensate for a static torque component, a principle known as static balancing. The conclusion of all this: for high-frequency inertial loads, the series topology is more energy efficient, but when there's a significant average torque component, parallel springs gain the upper hand. On to the next topic, redundancy. In mechatronics and robotics, torques and speeds typically vary throughout operating cycles. Because the efficiency of motors and gearboxes is also torque and speed dependent, this means that the efficiency of the drivetrain will vary over time. And so, inevitably, there will be instances when drivetrain efficiency will be very low. This typically happens when the motor is providing an output power way below its nominal power. Here, it would be more efficient to use a smaller motor. The concept behind redundancy is simple. We just use multiple smaller motors instead of one large motor. The idea is to make the motors work together, operating each at the combination of speed and torque that leads to the lowest energy consumption overall. The additional degrees of freedom granted by the redundant motors allow us to accomplish this. One way of building a redundant actuator is to couple motors to the same output by means of a planetary differential. This actuator is what we call kinematically redundant. The output speed is a weighted sum of the two motor speeds, so we have an infinite number of options to generate any output speed. Statically, however, the actuator is determinate. The output torque fully determines the motor torques. If we also add brakes to the different branches, we can choose to only work with one of both motors. This further increases the actuator's energy efficiency and, more importantly, extends the actuator's operating range. We built such an actuator and compared it to a regular servo motor with a similar torque and speed range. In experiments at steady state as well as in dynamic experiments, the dual motor actuator proved to be more energy efficient than its single motor equivalent. We also made a preliminary calculation of how such an actuator would do in an active ankle prosthesis as a replacement for the motor of a series elastic actuator. Our results show that a dual motor actuator would enable a 16% decrease in energy consumption, and that goes on top of the decrease that was already obtained with the series spring. In my PhD thesis, I uncovered many of the fundamental principles behind elasticity and redundancy in actuation, but there are still many challenges to be overcome. As a visiting postdoc here at the University of Tulsa, I'm addressing one of these challenges by developing feedback control algorithms for the muscle-like actuator. The ultimate dream: to develop an actuator that can compete with the human muscle in terms of energy efficiency, force density, and versatility. Such devices will be key enablers for technologies which interact in a safe and intuitive way with humans, such as active prosthetics and collaborative robots. And these devices, I believe, will change many people's lives in a positive way. And it's such a future that I'd be happy to contribute to.